As we were discussing earlier in the previous lecture, the simplifying idealizations that are typically employed in mathematical modeling of real or practical building frames that are three-dimensional in reality for the purposes of structural analysis uh, are generally implemented with the objective of simplifying the structural analysis and the structural design process for the real or practical building frames. Now, as I mentioned earlier, the second idealizing assumption that was implemented in the mathematical modeling of 3D building frames was based on the discretization of the three-dimensional idealized building frame model shown on the left hand side of this figure into a series of equivalent two-dimensional or plane frame models. For example, frames 1-1, frame 2-2, and frame 3-3 spanning along the x direction and therefore assumed to be resisting the lateral loads such as wind loads and earthquake loads acting in the x direction. Whereas the idealized three-dimensional frame model, also commonly known as the space frame model, shown on the left-hand side of this figure, is also discretized into a series of equivalent two-dimensional or plane frame models along the y direction. Where x and y are the two orthogonal horizontal coordinates that have been adopted for the structural analysis of the three-dimensional building frame. And therefore, the individual two-dimensional or plane frame models that are obtained by discretizing the original three-dimensional or space frame model into a series of equivalent plane frame models or two-dimensional frame models along the y direction, named as frame AA, BB and frame CC as shown on the right hand side of the figure are assumed to resist the horizontal or lateral loads such as the earthquake loads EL1, EL2 and EL3 and 4 acting on the floor masses through the center of mass of the respective floor in the horizontal y direction. Well, as we have discussed earlier, the simplifying idealizations that we have employed in the mathematical modeling of real or practical building frames, which in reality are three-dimensional or solid structures, into 3D frame models that are idealized by representing the original solid frame elements such as the beam elements and column elements, which are solid entities in reality, as well as further simplification of the idealized 3D or the space frame model shown on the left hand side of the figure into a series of equivalent two-dimensional or plane frame models along the two horizontal orthogonal directions x and the horizontal orthogonal direction y, is based on, or rather are based on, since we have employed three, or rather two simplifying idealizations or two levels of simplification by now, that is the simplifying idealization number 1 and number 2 that were discussed and presented in the earlier slides. And these simplifying idealizations number 1 and number 2 discussed and presented in the earlier slides and previous lectures are based on rational and realistic idealizing assumptions and are warranted or justified in view of the computational advantages or the simplicity that they offer in the structural analysis and design process of building frames in general and reinforced concrete building frame structures in particular. For example, the incentive or the advantage that is offered by the discretization of the original, or rather the idealized three-dimensional or space frame model with the individual frame elements that are solid entities in reality as equivalent line elements into series of equivalent 2D or plane frame models along the x direction, such as plane frame models 1, 1, 2, 2 and 3, 3 spanning in the x direction, and lying in the xz plane, as well as the discretization of the idealized 3D or space frame model shown on the left hand side of the figure into a series of equivalent two-dimensional or plane frame models spanning in the other horizontal orthogonal direction y, such as frames AA, BB and CC, with the frames lying in the YZ plane, results in substantial savings in the computational time and resources that are required to solve for the unknown displacements and the or degrees of freedom and the unknown internal actions, since the number of degrees of freedom in any or each of these equivalent to dimensional or plane frame models is only 27, whereas the number of degrees of freedom in the idealized three-dimensional or space frame model shown on the left hand side, as we presented earlier, are 162 unknown displacements or degrees of freedom, thus resulting in a stiffness matrix of the size 162 by 62, 162 square, that is 162 into 162 size stiffness matrix for the idealized 3D frame model or space frame model shown on the left hand side of this figure, which is quite a large stiffness matrix, considering that the stiffness matrix has to be inverted to determine the unknown displacements and therefore the unknown internal actions in the stiffness method of structural analysis of statically indeterminate frames. On the other hand, if we consider any of these individual equivalent 2D or plane frame models such as frame models AA, BB and CC obtained by discretization along the y-axis, or frames 1, 1, 2, 2 and 3, 3 obtained by discretization of the idealized 3D frame model along the horizontal orthogonal x-axis present only 27 unknown degrees of freedom in themselves, each in themselves. So, therefore, the size of the stiffness matrix that has to be inverted to solve for the unknown internal actions or the unknown degrees of freedom in any or each of these individual equivalent two-dimensional or plane frame models is only 27 by 27, thus resulting in considerable savings in the computational time and effort. Well, more importantly, or fundamentally, the benefit of the simplifying idealizations 1 and 2 discussed earlier, that are based on the discretization of the original building frame into a three-dimensional building frame model shown on the left hand side into series of equivalent two-dimensional or plane frame models along the two horizontal or orthogonal directions x and y, is that the discretization of the idealized three-dimensional or space frame model into individual or rather series of equivalent 2D or plane frame models enables the structural engineer to visualize the structural action or the load resisting mechanism of the original three-dimensional building frame in a more lucid and effective manner. In other words, the discretization or the simplifying idealizations 1 and 2 that were discussed in the previous lectures, presented in the earlier slide, are more amenable to physical understanding or physical interpretation of the load resisting mechanism, that is the path of load transfer for the vertical gravity loads denoted as VL, as well as the lateral or horizontal environmental loads such as the wind loads represented as the wind pressure PW and the earthquake loads denoted as EL acting on the floor masses. Therefore, the incentive or rationale or the advantage that is offered by the simplifying idealization number 2 involving the discretization of the original three-dimensional idealized 3D frame model shown on the left hand side of the figure into the individual or rather series of equivalent two-dimensional frame models is much more profound in terms of the engineering intuition and learning of the load resisting mechanism or the path of load transfer from the point of application of the externally applied loads to the support reactions or supports as the simplifying idealization provides an intuitive insight into the load resisting mechanism or the structural frame action, particularly the moment resisting structural frame action in case of moment resisting frames, or simply the path of load transfer or path of transfer of the externally applied loads in common language to the supports or the foundations represented as the fixed supports, which otherwise would not be so intuitive or apparent if we consider the three-dimensional building frame that exists or is constructed in the field in reality, or even the idealized 3D frame model shown on the left hand side of the figure. So to conclude, the simplifying idealizations number 1 and 2 that we discussed prior to this lecture or this slide and was presented in the earlier slides enable the structural engineer to gain a physical understanding or intuition or physical interpretation of the structural action in particular the structural moment resisting frame action of the original building frame, as well as a physical understanding of the path of transfer of loads from the point of application of the externally applied loads such as the gravity loads and the horizontal or lateral environmental loads, for example the wind loads and the earthquake loads. Thus enabling the structural engineer to verify the accuracy of the computational results that are output by structural analysis and design software. That may be employed to perform the computational structural analysis and design of the original building frame using the idealized 3D or space frame model shown here on the left hand side of the figure. Well, I may add that in the absence of such a physical understanding or engineering intuition of the structural behavior or the load resisting mechanism and the path of load transfer for the real or actual three-dimensional building frame, the structural engineer will be at a loss to verify the accuracy of the computational output from the computational structural analysis and design of the original 3D building frame or the idealized 3D or space frame model due to the lack of physical interpretation that is provided by the analysis of the idealized equivalent 2D or plane frame models. obtained as a result of the second simplifying idealization discussed in the previous lecture. As a conclusion, therefore, the manual analysis or even computational analysis of the equivalent 2D or plane frame models is of fundamental importance from the point of view of physical understanding of the structural behavior or the structural action or the load resisting mechanism of the 3D building frame, as well as for the purposes of verification of the computational output from the computational structural analysis and design of the idealized three-dimensional frame model using any commercial structural analysis and design software. Well, as we discussed earlier, the next step after the formulation of the mathematical model for the 3D building frame for purposes of structural analysis is the calculation or characterization of the externally applied external loads such as the gravity loads, the vertical gravity loads shown in acting on the top floor or the roof of this 4-story building frame shown in 3 dimensions, the wind load shown acting as a wind pressure denoted as PW, and the earthquake loads denoted as EL, which act as inertial forces through the center of mass of each floor mass. And in order to understand the calculation, the structural design philosophy underlying the design calculations for the external loads acting on 3-dimensional building frames, one needs to have a rational understanding and insight into the characterization of the external loads such as the vertical gravity loads denoted as VL and the lateral horizontal environmental loads such as the wind pressure, the wind loading due to the wind pressure denoted as PW, and the lateral or horizontal earthquake loads denoted as EL, acting through the center of mass of the floors of the 3-dimensional building frame. Now, the understanding and insight into the characterization of the external loads for the purposes of calculating the design loads that are to be considered in the structural analysis of the mathematical model or the idealized three-dimensional frame model, also known as the space frame model, shown on the left hand side of this figure. One needs to understand and visualize the mechanism by which these loads imposed by external effects or termed as external loads are, and in order to understand or visualize the mechanism of the action of the external loads, such as the vertical gravity loads and the lateral wind loads and earthquake loads, we will have a brief discussion on the mechanism of the action of the load as well as the load resisting mechanism of the building frame in three dimensions in reality, and the path of load transfer, from the point of application of the external load on the real or practical building frame in three dimensions to the supports or the foundations at the supports of the three-dimensional building frame. So as we were discussing the structural action of the idealized three-dimensional frame model, more popularly known as the space frame model, representing the actual or real three-dimensional building frame that is constructed in the field. In order to understand and visualize the mechanism by which the externally applied loads due to external effects such as vertical gravity loads, the lateral or horizontal wind loads, and the lateral or horizontal earthquake loads, one needs to intuitively consider the path of the load transfer of the external loads just mentioned from the point of application of such loads on the original three-dimensional building frame to the foundations or the supports of the original or practical three-dimensional building frame. And the simplifying idealization that are implemented in the mathematical modeling or characterization of the external loads on the idealized three-dimensional building frame model shown in the previous slide is based on the intuitive characterization as well as the physical load transfer path for the external loads acting on the real or practical building frame in the three dimensions. Therefore, in order to intuitively understand and visualize the mechanism of the action of the external loads on the original or practical three-dimensional building frame, one has to visualize the physical path of load transfer for the external loads that act on the real or practical building frame in three dimensions, as well as the structural behavior or structural response of the real or practical building frame in three dimensions under the action of the externally applied loads, which in engineering terminology is referred to as the load resisting mechanism of the building frame. Now, the load resisting mechanism of the building frame is of fundamental importance for the purposes of mathematical modeling and characterization of the external loads on the idealized 3D frame model or the original or practical 3D building frames for the purposes of structural analysis of the idealized three-dimensional frame model, more popularly known as the space frame model shown in the previous slide. Therefore, for the purposes of the mathematical modeling and characterization of the external loads, we will discuss the simplifying idealizations that are employed in the mathematical modeling and characterization of different types of external loads, such as vertical gravity loads, horizontal earthquake loads, and horizontal wind loads, for the purposes of calculating the design loading that is to be considered for the structural analysis of the idealized 3D frame model or the space frame model. So, starting with the vertical gravity loads, in order to characterize the vertical gravity loads acting on the real or actual three-dimensional building frame constructed in practice, we have to visualize the physical path of the load transfer for the externally applied vertical gravity load on the real or practical building frame constructed in 3 dimensions based on the following assumptions that are realistic and admissible for the purposes of calculating the external loads due to vertical gravity effects on the idealized 3D frame model or the space frame model. Well, the assumptions that are realistic and admissible for distributing the externally applied vertical gravity loads from the idealized 3D frame model or the space frame model to the equivalent 2D plane frame models for simplified 2D analysis are as follows. 1. Vertical gravity loads shown and denoted as VL in the figure of the idealized three-dimensional or space frame model on the left hand side of the previous slide. Due to the dead loads DL and the live loads LL acting on the floor slabs are transferred from the floor slab to the beams and in turn to the columns by the frame action. The second assumption that is also realistic and admissible for the purposes of characterizing, calculating and distributing the externally applied vertical gravity loads from the three-dimensional building frame model or the space frame model to the equivalent 2D planar frame models or the plane frames for the purposes of simplified two-dimensional structural analysis is that the vertical gravity loads that are acting on the tributary area of a beam. For example, area 1 area that is highlighted in the figure on the previous slide as area 1 is transmitted to the beam. In other words, the tributary area is defined as the area of the floor that contributes the distributed vertical gravity load to the beam. Therefore, the tributary area that contributes the distributed vertical gravity load to beam B1C1 is the trapezoidal area that is labeled as area 1. While the external gravity loads or the externally applied vertical gravity load VL acting on the triangular tributary area labeled as area 2 shown in the figure of the three-dimensional frame model or the space frame model on the left hand side of the previous slide is transmitted to beam C2, C3 of the idealized 2D frame, that is the plane frame CC. Therefore, to summarize the simplifying idealizations that are used for characterizing and distributing the vertical gravity loads acting on the idealized equivalent 2D frame models for structural analysis. The distributed vertical gravity loads VL due to the dead loads denoted as DL and live loads denoted as LL shown on the figure for the idealized 3D frame model or the space frame model on the left hand side of the previous slide are assumed to be distributed to the individual idealized 2D frame models or plane frame models in proportion to the tributary areas of the individual or idealized plane frames. And in case of floor slabs, that are rectangular in plan, the tributary area, that is the area, the floor area that contributes the vertical gravity load to the individual or idealized plane frame models would be trapezoidal. For example, the area designated as area 1 in case of the beam that resists the externally applied vertical gravity load, for example beam B1, C1, and the tributary area for the orthogonal beam, for example being C2, C3 in the idealized two-dimensional frame model CC or the plane frame CC will be triangular in case the floor slab is not a square floor slab but a rectangular floor slab. Well, with that we move on to the physical or intuitive visualization of the load transfer path for the horizontal or transverse loads, also termed as lateral loads due to the environmental factors such as earthquake and wind, in order to characterize and calculate the design earthquake, the design lateral loads due to earthquake or wind acting on the real or practical building frame in 3 dimensions that is constructed in the field for the purposes of structural analysis of the 3-dimensional, idealized 3-dimensional building frame model or the space frame model shown in the previous slide on the left hand side, as well as the idealized 2D frame models that are obtained by discretization of the idealized 3D or space frame model for simplified two-dimensional structural analysis. Well, in order to characterize or model the horizontal transfers or lateral loads due to the earthquake ground motion that act as inertial forces to the center of mass of the floor slabs, that is the center of gravity of the CG of the floor mass, one needs to understand the path of load transfer or the physical mechanism of the action of the earthquake or seismic forces. And in order to gain an understanding or insight into the physical path of load transfer for the externally applied earthquake loads, as well as the lateral load resisting mechanism or the horizontal load resisting mechanism of the real or practical building frame constructed in 3 dimensions, one needs to visualize the action, the mechanism of action of the earthquake loads that act as inertial forces on the individual floor masses due to the earthquake ground motion, as well as the lateral load resisting mechanism of the real or practical building frame constructed in 3 dimensions in the field with reference to the idealized 3-dimensional frame model, the space frame model shown in the previous slide on the left hand side. Therefore, the earthquake loads, that is the seismic forces due to the earthquake ground motion on the building frame act through the center of mass highlighted as CM of the floor slabs in common language, the center of mass is also referred to as the center of gravity of the floor mass. Since the earthquake loads act as inertial forces, the lateral loads or the horizontal transverse loads due to earthquake acting on the center of mass or through the center of mass of the floor slabs are assumed to be distributed or shared by the individual equivalent two-dimensional planar frames or plane frame models in proportion to the lateral stiffness of the individual 2D plane frame models spanning in the direction of the earthquake load. For example, the lateral earthquake load that is shared by or distributed to any 2D plane frame model or plane frame FF, for example, in the YZ plane of the idealized 3D building frame model or the space frame model shown on the left hand side of the previous slide, that is any plane frame F spanning in the Y direction at the level L can therefore be calculated as the total earthquake load denoted as EL at any level small l, the subscript small l signifies the level at which the earthquake load acts through the center of mass of the floor or the level times the stiffness of the frame under consideration, that is the stiffness of the idealized 2D plane frame model or plane frame F under consideration divided by the sum of the lateral stiffnesses of all the idealized 2D planar frames or plane frame models spanning in the Y direction as signified by the subscript Y. So, as an example, the lateral earthquake load EL that acts as an inertial force through the center of mass of each and every floor slab at any level L, small denoted as the subscript small l, is distributed to a plane frame F in the proportion of the lateral stiffness of the plane frame F spanning in the direction of the earthquake load acting at the level L of the floor mass where EL is the notation for the earthquake load acting on level L through the center of mass of the floor mass at the same level, small l, as shown in the figure on the left hand side of the previous slide for the idealized three-dimensional building frame model or the space frame model. In case of wind loads, the mechanism of action of the wind load is fundamentally different than that for the earthquake loads. In contrast to earthquake loads, which act as inertial forces through the center of mass of the individual floor masses or floor slabs, that is the center of gravity of the floor mass, the wind load acts as an or manifests as a wind pressure acting on the windward face of the building frame. For example, in the figure shown on the previous slide, the wind pressure denoted as PW, P subscript W. Subscript W signifies wind while P signifies pressure. Acting on the windward face, that is the YZ face of the idealized three-dimensional building frame model or the space frame model shown in the figure on the previous slide on the left hand side, or any part of the YZ face, for example the YZ face of any floor, that is the windward face of any floor, or level Y, level L is assumed to be distributed to or shared by any one two-dimensional plane frame models or plane frames F, in this case F, subscript F can range from 1 to 3, since there are 3 individual idealized 2D planar frame models or plane frame models spanning in the x direction, that is perpendicular or orthogonal to the windward face or the YZ face of the three-dimensional building frame model. The wind load, therefore, that acts as a wind pressure on the windward face, that is the YZ face of the idealized three-dimensional building frame model or space frame model shown in the figure on the left hand side of the previous slide, is distributed or shared by any of the individual idealized 2D planar frame or plane frames. F in the XZ plane, for example, plane frames 1, 1, 2, 2 or 3, 3 spanning in the X direction, can therefore be calculated based on the assumption that the force resultant of the wind pressure acting on the windward face or the YZ face of the 3D building frame is distributed to any of the idealized 2D or plane frame models numbered F, where F can be 1, 2 or 3, in proportion to the lateral or horizontal stiffness of the idealized plane frame model F. Denoted as Kf. In the plane, that is the stiffness K of the plane frame F in the plane XZ or the lateral stiffness of the plane frame F along the spanning in the X direction. Where WLL is the wind force resultant, or the resultant of the wind pressure acting at any level small l as shown in the figure on the previous slide. Well, to summarize the discussion till the previous slide, let us formally state all the inherent assumptions that have been adopted in the simplifying idealizations number 1 2, and 3 for the mathematical modeling of practical three-dimensional building frames for purposes of structural analysis of the frame model or the mathematical model in order to complete the structural design process of the real or actual three-dimensional building frames that are constructed in practice. Well, the first inherent assumption that is adopted in the simplifying idealization number 1 is that the brick masonry infill panels that are the filler walls that are implemented to fill the hollow spaces in the reinforced concrete building frame for practical or functional purposes of thermal insulation, sound insulation, and cladding only introduce or add a dead load on the structural frame, but do not otherwise participate in the structural action or the load resisting mechanism of the building frame. However, one should note that neglecting or ignoring the structural action of the masonry infills or the filler walls, that is the brick infill panels, may be unconservative for the purposes of calculating the earthquake loads, in which case the structural contribution of the brick infill panels in a masonry infilled reinforced concrete frame should be considered by explicit structural modeling of the brick masonry panel. Another implicit assumption in the simplifying idealization number 1 is that the characteristic or geometric properties such as the cross-sectional area, second moments of area or the moments of inertia, and the rotational or torsional moments of area that are assigned to the equivalent line elements in the idealized three-dimensional building frame model or the space frame model adequately characterize or represent the actual behavior of the solid frame elements that the line elements or the idealized line elements represent. Another inherent assumption that is made in the simplifying idealizations for mathematical modeling of real or practical 3D building frames that are constructed in the field for the purposes of structural analysis of the mathematical model or the idealized frame model in the structural design process of reinforced concrete framed building structures is that the assumption underlying the simplifying idealization 2 can be stated as that the equivalent two-dimensional frame models or the plane frame models that are obtained by discretization or decomposition of the idealized 3D building frame model, also known as the space frame model, in the two horizontal directions x and y that are orthogonal to each other, provide independent frame action in their respective planes, and thus can be analyzed independently as individual two-dimensional frame models or individual plane frame models. This assumption is realistic provided the vertical gravity loads due to the dead loads and live loads, for example, and the lateral or horizontal loads due to earthquake or wind loading, for example, acting on the original three-dimensional building frame model or the space frame model are distributed to the individual two-dimensional frame models or plane frame models using a rational approach for calculating the external loads shared by the individual plane frame models, that is based on the physical path of load transfer and a rational and realistic load resisting mechanism of the frame structure. As discussed in the previous slide, the physical path of the load transfer through the frame, building frame, is in the sequence of floor slabs to beams, beams to columns, and columns to the foundation. Therefore, the load resisting mechanism that is visualized for the three-dimensional building frame model or the space frame model should be a rational characterization of the physical path of the load transfer. In other words, the load resisting mechanism or the physical path of load transfer in the building frame should be rationally represented and modeled or accounted by the individual, by the distribution of the vertical gravity loads as well as the horizontal earthquake and wind loads acting on the original three-dimensional building frame to the individual two-dimensional frame models obtained by discretization of the original three-dimensional building frame. Then an inherent assumption underlying the simplifying idealization number 3, that is the idealization of the distribution of the external loads such as the vertical gravity loads due to dead load and live load, and the lateral or horizontal environmental loads due to the earthquake or wind loading. For example, from the original three-dimensional building frame characterized or modeled as uniformly distributed loads or distributed loads or concentrated loads acting on the idealized three-dimensional frame model or the space frame model. And the simplifying idealization 3 is inherently based on the assumption that the lateral external loads or the horizontal external loads due to wind or earthquake loading or their horizontal components acting in any horizontal or orthogonal direction X or Y are collectively resisted or shared by the equivalent two-dimensional plane frame models, or simply the individual plane frame models spanning in the respective orthogonal horizontal direction X or Y respectively. Another implicit assumption underlying the simplifying idealization number 3 is that the lateral load or the horizontal external load due to earthquake or wind loading, for example, that is shared by any or each of the individual equivalent two-dimensional frame models, also known as equivalent plane frame models, is proportional to the horizontal or lateral stiffness of the equivalent two-dimensional frame model or the plane frame model spanning in the direction horizontal and orthogonal direction X or Y in which the horizontal external load acts. Therefore, the share of any horizontal or lateral external load due to earthquake or wind loading, for example, acting in any one of the two horizontal orthogonal directions X or Y, that is resisted by any individual two-dimensional frame models or plane frame models spanning in that direction X or Y respectively, is proportional to the horizontal stiffness or the lateral stiffness of the equivalent individual two-dimensional frame model or the individual plane frame model, assuming or only if the floor slabs are constructed as rigid slabs or rigid diaphragms, that is, the floor slabs are infinitely rigid in their own plane as well as out of their plane, as in case of reinforced concrete floor slabs with thickness greater than 90 to 100 mm, in which case the assumption of the floor slabs acting as rigid diaphragms is a realistic assumption. So to conclude, IS 456 2000 revision, as per clause 22.4 of the Indian Standard Code of Design Practice for structural design of reinforced concrete elements, permits the simplifying idealizations 1, 2 and 3 for mathematical modeling of practical or real reinforced concrete building frames constructed in the field for the purposes of structural analysis under the action of vertical gravity loads. For purposes of structural analysis under the action of lateral or horizontal loads, the simplifying idealizations 1 to 3 are permitted or are permissible for application only in case of symmetrical building structures, that are building frames that are symmetric in both plan and elevation and do not exhibit any horizontal or vertical irregularity, and are not excessively tall with the limiting height as 90 meters for eligibility of application of the simplifying idealizations 1, 2 and 3. IS 456 2000 recommends that in case of building frames that are unsymmetrical either in plan or in elevation, or display a plan or vertical irregularity, that is horizontal or irregularity in plan or vertical irregularity in elevation, or are taller than 90 meters, more rigorous and advanced structural modeling and analysis methods should be employed for the structural design process of such building frames. In other words, the simplifying idealizations 1, 2 and 3 are permitted for most of the practical building frames that are constructed in the industry, since most practical building frames in reality are generally symmetrical in plan and elevation, as well as regular uh, in the vertical and horizontal direction, and generally real or actual building frames constructed in the Indian construction industry are less than 90 meters in height, that is less than 30 stories high. So therefore the simplifying idealizations 1, 2 and 3 are typically permissible as per the Indian standard code of design practice for structural design of reinforced concrete structures, IS 456 2000. For most or majority of real or actual reinforced concrete building frames that are constructed in practice in India, there is another simplifying idealization that is employed for mathematical modeling of three-dimensional building frames for the purposes of structural analysis in the structural design process of only reinforced concrete frame building structures. That is, simplifying idealization number 4 that we'll discuss today is applicable or valid or required only for the mathematical modeling of reinforced concrete three-dimensional building frames for the same purpose of the structural analysis of the mathematical model or the idealized frame model in order to complete the structural design process for reinforced concrete frame building structures. And the simplifying idealization number 4 that is implemented in mathematical modeling of reinforced concrete building frames only is based on the definition of the geometric properties of the reinforced concrete or RC frame elements. That is, the representative geometric properties or the characteristic geometric properties that are assigned to the line elements in a idealized 3D building frame model of a reinforced concrete frame building structure constructed in reality is calculated on the basis of any one of the following definitions of the concrete section. And the definitions that are generally implemented or utilized for assigning the characteristic or representative geometric properties to the idealized line elements in an idealized three-dimensional or even two-dimensional building frame model for the purposes of structural analysis of the original reinforced concrete frame building structure constructed in practice are presented in their ascending order of their accuracy. The first definition of the geometric properties of reinforced concrete frame elements is based on the nominal or gross concrete section. And as the name suggests, the geometric property, the definition of the concrete section for calculating the characteristic or representative geometric property of the respective RC frame element is the overall concrete section, ignoring the steel reinforcement. In other words, the gross concrete section or the nominal concrete section, as it is also referred to, is defined as the total concrete section shown in this figure, that is the overall concrete section, simply ignoring the steel reinforcement. Therefore, considering this typical cross-section of a reinforced concrete frame element such as a reinforced concrete beam or a reinforced concrete column, based on the definition of the concrete section as a nominal or gross concrete section, the characteristic or representative geometric properties of the typical reinforced concrete section shown in this figure may be calculated as the gross area, A subscript gross, which, based on the definition of the concrete section as a gross concrete section or nominal concrete section, is simply computed as the width B times the overall depth D, thus ignoring the area or the mechanical properties of the steel reinforcement that are actually provided in a typical reinforced concrete section in reality. And based on the nominal or gross concrete section as for the definition of the characteristic or representative geometric properties that are assigned to the idealized line element, the moment of inertia or the second moment of area Iyy with the y axis, yy being the major axis of the reinforced concrete section as shown in this figure for a typical reinforced concrete section with width b and overall depth d. The moment of inertia or the second moment of area of the concrete section based on the nominal or gross section is calculated as I2, where I2, the subscript 2 signifies the second moment of area, I is the notation for moment of inertia, and therefore the moment of inertia Iyy or the second moment of area I2 about the major axis yy of the concrete section shown in this figure for a typical reinforced concrete section is BD cubed by 12, as it is apparent intuitively that the contribution of the reinforced steel reinforcement or the reinforcing steel which is present in the reinforced concrete section typically is simply ignored in the definition of the moment of inertia or the second moment of area based on the nominal or gross concrete section. So therefore, as mentioned earlier, the definition of the characteristic or representative geometric properties assigned to the idealized line elements representing, modeling the actual solid reinforced concrete elements in the original reinforced concrete frame building structures based on the gross or the nominal concrete section is approximate and is the least accurate, although sufficiently realistic, but in terms of accuracy, the gross concrete section or the nominal concrete section results in the least accuracy in the calculation of the geometric properties such as gross area or nominal area or the gross moment of inertia or the nominal or the moment of inertia, that is the second moment of area based on the gross or nominal concrete section. A more accurate or more precise definition of the concrete section, such as the typical reinforced concrete section shown in this figure, is based on the transformed or equivalent concrete section. And the definition of transformed or equivalent concrete section is one that is characterized or modeled as the sum of the contribution of the concrete area and the equivalent steel area, transformed by multiplying the steel area with the modular ratio M, where M is the ratio of the moduli of elasticity of steel to that of concrete. That is ES by EC, where the ratio ES by EC is defined as the modular ratio, where subscripts S and C signify steel and concrete. And based on the definition of the transformed or equivalent concrete section, the geometric properties that need to be considered or assigned for the idealized line elements representing the actual or real solid 3D elements in the practical reinforced concrete frame building structure may be calculated using the definition of transformed or equivalent concrete section as the transformed or equivalent concrete area, transformed or equivalent area of the cross section, A tran, where subscript tran signifies the transformed or equivalent concrete section, and the area of the transformed or equivalent concrete section is therefore by definition calculated as B times D, that is the width times the overall depth, which is the concrete area, overall area of the cross section, also the gross concrete section or the nominal concrete section, plus M minus 1 times the sum of the area of steel reinforcement in the tensile zone and the area of the steel reinforcement in the compression zone, where AS denotes the area of tension steel, that is the area of reinforcing steel in the tension zone of the cross section, and A dash S denotes the area of the steel reinforcement or reinforcing steel in the compression zone as shown in this figure. Subscript S simply signifies steel, which may be in the compression zone with an area A-S, or maybe in the tension zone, typically denoted as A subscript S. In general, a typical reinforced concrete section will have both compression and tension steel, that is A-S with areas A- subscript S and A subscript S. And the minus one, the only figure, or the only value that needs explanation in this formulation for the equivalent or transform formulation of the area based on equivalent or transform concrete section is the minus one here. The minus one in the coefficient m minus 1 is included to account for the fact that the steel area, the area of the reinforcing steel in the tension zone as well as the compression zone has already been considered in the term B times D, that is the gross or concrete area, and therefore should be subtracted so that the total steel area AS plus AS dash is not accounted twice. The calculation of the other geometric property that is required, which is the second moment of area or the moment of inertia based on the definition of transformed concrete section, can be obtained by replacing the steel area in the compression zone by an equivalent concrete area equal to m minus 1 times A dash S, and the steel area in the tension zone also by m minus 1 times the steel area in the tension zone. So the geometric property or that is characteristic or representative of the original solid reinforced concrete frame element, beam element or column element based on the definition of transformed or equivalent concrete section is more accurate or more precise than that based on the definition of gross concrete section or nominal concrete section. Since the geometric property, for example, the cross-sectional area and the second moment of area or the moment of inertia that is calculated based on the definition of transformed or equivalent concrete section for a typical reinforced concrete section with compression and tension steel both, is calculated by substituting the tension and compression steel by an equivalent or transformed concrete area shown by this dashed rectangle, obtained as the modular ratio times the area of the compression steel and the modular ratio times the area of the tension steel, thus accounting for the different mechanical properties of steel and concrete in a typical reinforced concrete section. And considering the enhancement of the moment of inertia as well as the area due to the presence of reinforcing steel in the compression zone as well as the tension zone, by adding the actual stiffness, actual stiffness of the steel based on the modulus of elasticity of steel, which is much higher, typically 7 to 10 times that the modulus of elasticity of concrete. Finally, the most accurate, or rather proceeding in the ascending order of accuracy, finally the most accurate definition of the concrete section for calculating the characteristic or representative geometric properties that are assigned to the idealized line elements representing the actual or real solid reinforced concrete frame elements in a reinforced concrete frame building structure is the definition based on the equivalent cracked concrete section, which not only accounts for the contribution or enhancement of the geometric property due to the contribution of the steel, as in case of the previous definition of transformed or equivalent concrete section, but also accounts for the fact that typically reinforced concrete sections, in case of reinforced concrete framed building structures, are cracked under service loads or in the working range of loads or the service range of loads. The cross section of the reinforced concrete frame element is generally cracked under working loads or service loads. and therefore part of the concrete section that is below the neutral axis being cracked is ineffective in tension, and therefore strictly the concrete section below the neutral axis that is cracked should not be considered or should be neglected in the calculation of the characteristic geometric properties such as the area and the moment of inertia or the second moments of area. So therefore, based on the definition of equivalent cracked concrete section, that is the sum of the uncracked concrete only the concrete above the neutral axis and the transformed steel area obtained by multiplying the steel area by the modular ratio is the most accurate definition of the concrete section. In reality, for reinforced concrete frame building structures that are constructed in practice under the action of service loads. Therefore, to conclude, the characteristic or representative geometric properties that are assigned to the idealized line elements representing the original or actual solid frame elements in a reinforced concrete frame building structure calculated on the basis of the equivalent concrete section can be formulated as follows, or as shown as mentioned in this slide. The area of concrete area of cross section of for a typical reinforced concrete section in RC frame elements such as a beam or column may be calculated as on the basis of the definition of equivalent cracked concrete section as B times C, where C is the neutral axis, the depth of the neutral axis, below which the cracked concrete is ignored for the purposes of calculating the geometric property. Note that C is typically less than the overall depth, is generally much less than the overall depth in a practical reinforced concrete frame element, especially beam elements. And so therefore, substituting the depth of the neutral axis C in place of the overall depth capital D in the cross-sectional area results in a more accurate characterization of the effective concrete section, that is the concrete. Today we will summarize the structural design process, including the first principles of mechanics that were implemented for mathematical modeling of reinforced concrete frame building structures, and the methodology of simplification of the structural analysis, mathematical models for the purposes of determining the internal actions in the individual frame elements of the reinforced concrete building frames as part of the structural design process for reinforced concrete frame building structures. In conformity with the Indian Standard Code of Practice for structural design of reinforced concrete structures, and the structural analysis and design methodology for reinforced concrete frames may be summarized by the following steps as a review or recap of the previous lectures till this point of time. First step is the mathematical modeling of the reinforced concrete building frame that is constructed in practice as a three-dimensional solid building frame in practice with solid frame elements in reality by idealizing the solid frame elements as equivalent line elements for the purposes of formulating the idealized three-dimensional frame model or the space frame model with line elements representing the original solid frame elements in the reinforced concrete building framed structure that is constructed in the field. The second step, as we discussed earlier, is the discretization or the simplification of the idealized three-dimensional frame model with line elements, popularly known as the space frame model, into a series of idealized 2D frame models, more commonly termed as plane frame models, for equivalent two-dimensional analysis. For example, plane frames 1, 1, 2, 2 and 3, 3 in the YZ plane, spanning in the Y direction, as shown in the figure of the idealized three-dimensional frame model or the space frame model in the previous slide, as well as the idealized 2D frame models or planar frame models AA, BB and CC, lying in the XZ plane and spanning in the X direction, as shown in the same figure for the idealized three-dimensional frame model referred to as the space frame model in the terminology of structural analysis. The third step in the structural design process for reinforced concrete frame building structures, subsequent to the formulation of the idealized frame models, whether in 3 dimensions or in 2 dimensions, that is space frames or plane frames, is to calculate or compute the design loading acting on the idealized 3-dimensional frame model or the space frame model by considering the following design loads that are specified by the Indian Standard Code of Practice for calculation of design loads, IS 875 2015, the latest revision, and the design loading that is to be considered for the structural analysis of the idealized frame models formulated as the mathematical models for the original reinforced concrete frame building structures constructed in practice are: 1. Dead load, that is specified by IS 875 Part 1, latest revision of which was published in 2015. So the 2015 revision of IS 875 Part 1 has to be considered for calculating the dead loads on the idealized 3-dimensional frame model or the space frame model. And as we can intuitively visualize, the dead load are due to our gravity loads that act on the building frame due to the self weight of the building components. The second type of design loading that needs to be considered in the structural design process of reinforced concrete frame building structures are the live loads, also referred to as the superimposed loads or imposed loads, that are provided by IS 875 Part 2, the latest revision of which is published in 2015 and is to be considered for computing the design live loads on the idealized 3-dimensional frame model or the space frame model shown in the figure of the idealized space frame model in an earlier slide. And as one can intuitively visualize, the live loads or the imposed loads are gravity loads that act in the vertical direction due to the weight of the users and contents, that is due to the use or occupancy of the building. The third type of design loading that needs to be considered in the structural analysis of the idealized three-dimensional frame model or space frame model is fundamentally different from the earlier two types, that is the dead load and the live load. Since the dead loads and the live loads are vertical gravity loads that act by virtue of the weight and the gravity, or the gravitational weight, gravitational force due to the weight of the building components and the users or occupants of the building, as well as the contents of the building. The third type of design loading that we have listed in this slide is the wind load, which is an environmental load that acts as a wind pressure on the various faces of the building frame, and the wind load is provided by IS 875 Part 3, the latest revision of which was published in 2015 and should be considered for calculating the wind loads acting on the building frame due to the dynamic wind pressure on the surfaces of the building by calculating the force resultants of the horizontal component or the lateral component of the dynamic wind pressure. To summarize the discussion in this slide, the structural analysis of practical three-dimensional frame building structure is performed by analyzing, idealizing the three-dimensional building frame that is constructed in practice as a simplified, idealized three-dimensional building frame model or a space frame model, as the three-dimensional building frame model is popularly known, with line elements representing the original reinforced concrete, solid frame elements in the original reinforced concrete frame building structure that is constructed in the practice or the field. In which case the analysis or the structural analysis of the reinforced concrete frame building structure will be three-dimensional. Alternatively, the structural analysis can be simplified to a two-dimensional or a plane frame analysis by discretizing the idealized three-dimensional frame model, more popularly known as the space frame model, into series of idealized two-dimensional frame models or plane frame models spanning in the two orthogonal horizontal directions x and y as explained in step 2. And in case of such an idealization, to simplify the three-dimensional or the space frame model into a series of equivalent two-dimensional or plane frame models by the discretization explained in step 2, the structural analysis and the mathematical model that is used for the structural analysis will both be two-dimensional. That is, the structural analysis will be a two-dimensional analysis involving the analysis of statically indeterminate two-dimensional frame models or plane frame models, and the analysis itself is referred to as plane frame analysis, since the mathematical model used for the structural analysis is a two-dimensional frame model or a plane frame model obtained by the discretization of the idealized 3D frame model. Continuing our discussion on the structural design process for reinforced concrete building frame structures that are constructed in practice, the third step, as we were discussing earlier, in the structural design process is the computation of the design loading that is to be considered to act on the reinforced concrete building frame structure for the purposes of the structural analysis of the mathematical model, that is the idealized three-dimensional frame model or the space frame model or the equivalent two-dimensional frame models or plane frame models as an alternative for simplification of the analysis. The fourth type of design loads that need to be considered for the structural analysis of the idealized three-dimensional frame model, popularly known as the space frame model, or the alternative equivalent two-dimensional frame models, also referred to as the plane frame models, are the earthquake loads that act on the reinforced concrete frame building structure as inertial forces due to the earthquake ground excitation, and therefore act through the center of mass of the individual floor masses in the original reinforced concrete frame building structure or the idealized three-dimensional building frame model as discussed earlier. The mechanism of the action of the earthquake forces or earthquake loads is fundamentally different from that of the wind loads, as earthquake loads are induced by the virtue of the ground acceleration due to the earthquake ground shaking, thus inducing inertial forces on the floor masses. And these inertial forces that are induced on the floor masses by the virtue of the ground accelerations due to earthquake ground shaking act through the center of mass of the floor masses shown in the figure of the idealized three-dimensional frame model or the space frame model in a previous slide. Well, the inertial forces that are induced as a result of the earthquake ground accelerations on the individual floor masses, for example M1, M2 and M3, are displayed in this figure as a schematic for visualizing the earthquake-induced inertial forces on the individual floor masses M1, M2 and M3 as shown in this figure because of the ground acceleration due to earthquake ground shaking shown as the red. Time history of earthquake ground excitation or the ground acceleration time history shown in red ink due to the earthquake ground shaking. The next type of design loads that need to be considered in the structural design process of reinforced concrete frame building structures that are constructed in practice, particularly in hilly regions with snowfall that are above the snow line, are the snow loads. And as the name suggests, snow loads are also vertical gravity loads that are caused by the weight of the accumulated snow on the building roof in hilly regions with snowfall that are specified by the Indian Standard Code of Practice IS 875 for calculation of design loads. Part 4 specifically addresses snow loading and the design loads due to snow loading are to be calculated and accounted in the structural design process as per the latest revision, that is the 2015 revision of IS 875 Part 4. In addition, in case of specialized structures, there are some additional external loads and effects that are characteristic of the specialized nature or the function of the specialized structure that should also be accounted in the structural design process for the reinforced concrete frame building structure, since in case of such special structures the additional loads and external effects that are characteristic of the specialized function of the structure are substantial and significant in comparison to the previously discussed design loads and therefore cannot be ignored. Examples of such additional external loads and effects that are characteristic of specialized structures with special functions are soil and hydrostatic pressures. For example, in case of earth retaining structures and liquid retaining structures, such as retaining walls, wherein the earth pressures are significant and therefore cannot be neglected and have to be considered in the design of such earth retaining structures, and water tanks, reservoirs, underground tanks, overhead water tanks, and similar liquid retaining structures wherein hydrostatic pressure is a significant component of the design loading that governs the structural design of the liquid retaining structure. Further, vibration loads due to reciprocating machinery is another example of additional external loads and effects that is characteristic of industrial structures, that are special structures constructed for housing reciprocating type machinery that induces significant vibration loads. Impact loads is another example of such additional loading effects that are characteristic of specialized structures that are provided with impact type machinery such as press, hydraulic press, or foundry. Further, fatigue due to repeated cyclic loading must be considered in case of structures or building structures wherein repeated cyclic loading and cyclic load reversals are dominant and persistent and may cause fatigue of the individual structural frame elements. An example of such repeated cyclic loading or cyclic load reversals that may result in fatigue of the individual frame elements in a reinforced concrete building frame structure is vibration loads due to reciprocating machinery or reciprocating type equipment that induces cyclic load reversals and repeated cyclic loading due to the vibrations of the reciprocating machinery, which may result in the fatigue of individual or specific frame elements in the reinforced concrete building frame structure. Then, moving on, foundation movements due to support settlements caused by various factors that are generally geotechnical should also be considered as additional effects or external loads that are induced by such movements of the foundation or support settlements. Another type of external load that may be predominant and governing in case of special structures are concentrated loads that act under special circumstances, for example, during the construction stage, and are therefore termed as construction loads, which cannot be ignored in the structural design of the reinforced concrete building frame structure, as the reinforced concrete building frame structure should be designed to resist any and all external load effects and special loading effects that may be predicted to act on the reinforced concrete building frame elements at any stage of the construction. To summarize the discussion on this slide, we have listed and discussed all the design loads, including vertical gravity loads and the horizontal environmental loads and special loads due to the specialized function of the building structure that need to be accounted in the structural analysis of the idealized building frame models whether three-dimensional or space frame models or two-dimensional or plane frame models. And the objective of the structural analysis, as we have mentioned earlier, is to determine the internal actions, that is the bending moments M, the axial forces P, and the shear forces V in the individual reinforced concrete structural frame elements for the purposes of the structural design process and completion of the structural design of the individual reinforced concrete frame elements such as the beams and the columns. After completing the step 4 in the structural design process for reinforced concrete building frame structures, that is, after completing the characterization and modeling of the externally applied loads due to external effects such as vertical gravity loads and the horizontal or lateral earthquake and wind loads, as well as calculating the design loading that is to be considered in the structural design of the reinforced concrete frame building structures. The next step, that is step number 4, in this step-by-step wise presented methodology for the structural design of reinforced concrete frame building structures is the structural analysis of the mathematical model or the idealized frame models that are derived or formulated in the step number 2 of the structural design process. Now here in step number 4 there are two options. Option number 1 is to perform a detailed or elaborate three-dimensional analysis of the idealized three-dimensional frame model under the action of the design loads calculated in step number 3. However, since 3D structural analysis, that is analysis of the idealized frame model in 3 dimensions, is a complex and time-consuming task from the point of view of the computational resources, the computational time and effort that is required to solve for the much larger number of unknown degrees of freedom in case of the three-dimensional frame model or the space frame model, wherein the number of unknown degrees of freedom for at each joint is 6, as we discussed earlier, and these 6 unknown degrees of freedom are the 3 deflections u, v and w along the x, y and z axis, and the 3 rotations theta x, theta y and theta z about the x, y and z axis respectively, thus resulting in a stiffness matrix with the dimension of 6 times the number of joints square, that is 6 times nj into 6 times nj, where nj is the number of joints with 6 degrees of freedom that are unknown and for each joint, and therefore have to be solved for by inverting the much larger stiffness matrix obtained in the 3-dimensional analysis of the idealized 3D frame model, or the more popularly known as the space frame model. A simpler option that requires much less computational resources in terms of computational time and effort, as well as is more amenable to physical interpretation or physical reasoning based on intuitive visualization of the results of the analysis in 2 dimensions, is the equivalent 2-dimensional structural analysis of the idealized 2D frame models or the plane frame models that are obtained by discretization of the detailed idealized 3-dimensional frame model or the space frame model into series of equivalent 2-dimensional frame models or plane frame models. And the reason, rather the practical reason, because of which a simplified equivalent 2D structural analysis of the idealized plane frame models may be preferred or may be necessary, is that not only does the simplified equivalent 2-dimensional analysis of the idealized 2D frame models or the plane frame models result in substantial savings in computational time and effort, but also allow the structural engineer or enable the user to intuitively visualize the physical significance of the results or the physical interpretation of the output from the detailed or elaborate 3-dimensional structural analysis of the idealized 3D frame model or the space frame model that may have been performed earlier for detailed analysis as option 1. In other words, the simplified equivalent two-dimensional analysis, that is the second option or option number 2 in the step 4, involving structural analysis of idealized frame models, lends itself to the physical understanding or intuitive understanding of the physical behavior of the real or practical reinforced concrete frame building structures. And the simplified equivalent two-dimensional structural analysis using the idealized 2D frame models or the plane frame models obtained by discretization of the detailed idealized 3D frame model or the space frame model into series of such equivalent 2D frame models or plane frame models in each of the two orthogonal directions x and y in the horizontal plane is more amenable to physical interpretation or visualization of the physical significance of the output or computational results for the unknown internal actions. Well, it is noteworthy to mention once again that in comparison to the detailed or elaborate three-dimensional structural analysis of the idealized 3D frame model or the space frame model, the equivalent of two-dimensional structural analysis of the idealized 2D frame models or the plane frame models present much fewer, much smaller stiffness matrix that is to be inverted to solve for the unknown degrees of freedom. Since the number of unknown degrees of freedom in case of a planar or two-dimensional structural analysis of a plane frame model are only 3 at each joint, and these are the unknown degrees of freedom at any and each joint being u, w and theta y, that is the deflections u and w along the x and z axis respectively, and one rotation theta y about the out of plane y axis of the plane frame, thus resulting in a total of 3 times nj as the number of unknowns for the plane frame model. Now, with the total number of unknown degrees of freedom for each and every plane frame model or two-dimensional frame model has 3 times the number of joints in J, the size of the stiffness matrix that needs to be inverted to complete the solution of the unknown degrees of freedom and therefore the unknown internal actions for any plane frame model is only 3 times nj square or 3 times nj into 3 times nj, where nj is the number of joints in the plane frame model, which, as you can compare with the 3-dimensional frame model or the space frame model, are much less. And therefore the dimension of the stiffness matrix in case of an equivalent 2-dimensional structural analysis of plane frame models presented to the user is 3 times nj into 3 times nj, which is much smaller than the dimension of the stiffness matrix that is presented for inversion in the detailed or elaborate 3-dimensional structural analysis of the idealized 3D frame model or the space frame model. Well, proceeding to the next step, after having completed the solution of the unknown degrees of freedom, or the unknown internal actions, by performing a detailed or elaborate 3-dimensional analysis as option 1, or a simplified or equivalent 2-dimensional analysis as an alternative option number 2. The next step, that is the step number 5 in the structural design process for reinforced concrete building structures, is the final step in the step-by-step structural design methodology that is presented in the 2 previous slides and the present slide. Step number 5 is the final step in which the individual structural frame elements, for example, the reinforced concrete beam and column elements or beam column elements, are designed to resist the internal actions, that is the bending moment M, the shear force V, and the axial force V acting at the 2 ends, as well as the interior of the, as well as the span of the structure frame elements. And the structural design of the individual structural frame elements, for example, the beam elements, reinforced concrete column elements, or the reinforced concrete beam column elements, to resist the internal actions M, V, and P, acting along the span of the individual structure frame elements. The structural design is performed in accordance with the provisions of IS 456 to 2000 revision, the Indian Standard Code of Design Practice for structural design of reinforced concrete structures.